Good afternoon, class. Today we're going to be talking about waves. Now, there are two ways to categorize your waves. First of all, they can be separated on the basis of their ability or inability to travel through empty space. It can be an electromagnetic wave which can travel through empty space because its waves are produced through the vibrations of charged particles. For example, a light wave. Or it can be classified as a mechanical wave, which can't travel through empty space as it needs a medium to transport its energy, like a sound wave, and that's why you can only hear sound in space. The other way in which you can classify waves is by the direction of the movement of the particles relative to the direction that the wave is moving. If the wave is longitudinal, the motion of the particles and disturbance are parallel to the direction of the wave. If it is transverse, the motion of the particles and the disturbance are perpendicular to the direction of the wave. Both of these types of waves are called periodic waves because they consist of repetitive cycles or patterns that are produced by the source.
Pictured above, you can see a transverse wave. If one end of the elongated spring is moved upwards, an upwards pulse moving towards the right will be created. If the same end of the spring is also moved downwards, a downward pulse moving towards the right will also be generated. If it is continually being moved up and down in simple harmonic motion, an entire wave will be produced. In the diagram below, we can see a longitudinal wave. At one end, the elongated spring is pushed forward in parallel towards its length and then pulled back to its original position. The compressed coils will be sent to travel towards the right. The same will happen when the spring is pulled back. Once again, if the spring is moved back and forth in simple harmonic motion, an entire wave will be created. When inspecting the transverse wave, you can notice that there are patterns that include special places called nodes and antinodes. Nodes are places that do not vibrate at all, and the antinodes are places where the maximum vibration occurs.
The equation to determine the speed of the wave is speed equals frequency times wavelength. If your frequency increases, your wavelength has to decrease. And if your wavelength increases, your frequency has to decrease. Now, the speed of the wave is only determined by the medium it travels through, such as air or water, and it is not dependent on the variables in this equation. As you can see in the diagram I have drawn, there are 4 points to every single wave: the crest, the trough, the wavelength, and the amplitude. Now, the crest is the highest point in the wave, the trough would be the lowest, the wavelength is the distance between two consecutive crests or troughs, and the amplitude is the maximum vertical extension from the point of equilibrium, which is the center area in the wave.
Interference within waves can occur when two waves are traveling along the same medium. There are two types of interferences: constructive interference and destructive interference. When two waves always meet crest to crest or trough to trough, they are said to be exactly in phase and exhibit constructive interference. As you can see in the diagram, both the waves have a displacement in the same direction, positive. When the two waves meet, their amplitudes will add together to create an amplitude equal to the sum of the existing waves' amplitudes. Constructive interference creates antinodes. When two waves meet crest to trough, they are considered to be exactly out of phase and exhibit destructive interference. As opposed to constructive waves, destructive waves have the displacement in the opposite direction, one positive and one negative. When the waves meet, the net effect is mutual cancellation. Destructive interferences create nodes.
As you can see, I have brought two identical tuning forks. I have taken multiple classes of Aikido, so I do know how to hit things. So what I'm going to do is I'm going to hit this first one, and you will see something called resonance.
When an object vibrates nearby or in contact with a second object, and the frequency of its vibration is near the natural frequencies of the second object will start to vibrate at its natural frequency. The fundamental frequency of a wave is also the first harmonic, whether it is a stretched string, open, or closed-ended cylinder. As you can see, for a stretched string, there's only one antinode and two nodes for the fundamental frequency. Therefore, the equation for the length is equal to 1/2 times the wavelength. When another antinode and node are added onto the wave, it becomes the first overtone and the second harmonic. The equation then becomes length equals 2/2 times the wavelength. As more nodes and antinodes are added to the wave, the overtone and the harmonic will increase by 1, and the numerator in the equation increases as well. For an open cylinder, the fundamental frequency has a single node as well as two antinodes. The equation for the fundamental frequency would be length equals 1/2 times the wavelength. When another antinode and node are added onto the wave, it becomes the first overtone and the second harmonic. The equation then becomes length equals 2/2 times the wavelength. As more nodes and antinodes are added to the wave, the overtone in the harmonic will increase by 1, and the numerator in the equation increases as well. Finally, for the closed-ended tube, it is slightly different from the other two in that the fundamental frequency has only one antinode and node, which is why the equation becomes length equals 1 over 4 times the wavelength. As you can see, the denominator of the fraction is 4 instead of 2. Also, when another node and antinode are added, it becomes the first overtone and the third harmonic instead of the second. Therefore, the numerator in the equation becomes a 3 instead of a 2 as expected. As you increase the number of nodes and antinodes, the harmonic and the numerator increase by 2 instead of 1 like in the other two examples shown. There are no even harmonics for closed-ended tubes.
Thank you for coming to today's class. That's the basics of waves and should get you ready for the Physics 1 AP test. It's time for me to wave goodbye, and I'll see you later.